Yeah, last time I stated the theorem, but also I'm not restated, but I need some notation which I also introduced last time. Let's go back. We're looking at a compact connected Lie group, and G its Lie algebra, GC its complexification, T maximal torus, and this T is its Lie algebra. Then we know that G decomposes as a direct sum T tends to C over R, which I denote TC, plus number of eigenspaces corresponding to non-trivial eigencharacters on T, delta next T, which is the group of characters on T, and G alpha is the eigenspace corresponding to that character, set of elements T in T, sorry, V in G, add T of V is alpha T times V. Delta is a set of non-trivial characters. The trivial character denoted by 0. Xt will be group operation, this will be additively written. So that was the decomposition. And then I introduced certain groups, namely I denoted by T plus, sorry, T plus sigma hold on, yeah, I denoted by, I hope I am seeing the correct notation. T alpha will be the identity connected component of kernel alpha. Alpha is a character, it's a mapping from T into the unit circle, and I look at the kernel, that will be obviously a closed subgroup of codimension 1, and I take the identity connected component. So this is a torus a one dimension less than that of T. And then I introduced the group ZT alpha, which is the centralized of T alpha, GT for every T alpha, centralized of T alpha. In fact, it's actually it is the identity connected component of this. In fact, it turns out that ZT alpha itself is connected. So you don't have to go to the connected component, it's connected. Why is this? This is because I proved long time ago the following proposition. Given a torus T in G and an element X in G commuting with all of T, there is a torus containing T, or I shouldn't call this T, maybe let me call it something else, because T I have fixed with the maximal torus, so let me say a torus B containing B and X. This will automatically prove that ZT alpha is connected, because take ZT alpha and take any point in it, that point together with T alpha will be contained in a torus. So, and that torus obviously centralizes T alpha, it's entirely inside ZT alpha. That element together with this is contained in a torus. That element, the entire torus commutes with T alpha, therefore it is in ZT alpha. And therefore, you have a connected torus containing any point which is in the centralizer of T alpha, connected torus containing T alpha, so it's clear that it's connected. So, ZT alpha is actually connected. So, apply this proposition, then you get this implies connected. Notice also that ZT alpha can also be, T alpha is a torus, so T alpha being a torus, let's me write the Lie algebra of T alpha will be T alpha, and then the centralizer of ZT alpha is also equal to set of G in G such that had G X equals X for every X in T alpha. In other words, this by definition, this is this set, this group is Z T alpha. The reason is, if G commutes with T alpha, it also commutes with exponential of every element in T alpha, which will generate entire T alpha. You take the Lie algebra of a torus and take exponentials of elements in that, they will be contained in Z alpha. If G commutes with ZT alpha, element of this, then it also commutes with the exponential. And therefore, the two things are the same. Of course, if something happens with T alpha, this happens with the real with the real algebra. So ZT alpha is equal to this. We also saw that ZT alpha can be written as is equal to any compact group we know is it's a simple group times the center of this T alpha, which is actually T alpha. It's an almost direct product of this kind. This is actually the commutator of T alpha with itself. So that is G alpha for you. We also saw that G alpha is of dimension 3. Its Lie algebra G alpha is okay, it's Lie algebra. Let's that it's Lie algebra with G alpha, and then G alpha tensor C over R is nothing but C E alpha plus C E minus alpha plus C H alpha, where E alpha is an element in G alpha, E minus alpha is in G minus alpha, and E alpha E minus alpha is H alpha. So, after tensoring with C, this Lie algebra of G alpha becomes nothing but SL2C. So, G alpha is isomorphic to SL2C, from which you see that this. So, dimension 3, we have seen that dimension 3 implies G alpha is isomorphic to SU2 or SO3. Either case, so there exists a morphism, a group homomorphism, an isomorphism, no, not an isomorphism, a group homomorphism phi alpha from G alpha to from SU2 to G alpha. This it's going to be an isomorphism if G alpha is isomorphic to SU2, but if it's SO3 then it will be a two-sheeted covering. If G alpha is isomorphic to SU2 and covering of order 2, if G alpha is isomorphic to SO3. In any case, there is a homomorphism from SU2 into the group onto the group G alpha. Notice that of course G alpha is connected because G alpha is connected and the commutator subgroup is therefore connected. Now, so we have this homomorphism phi alpha from SU2 to G alpha. The induced map phi alpha dot from the Lie algebra of SU2 tensor with C. Anyway, phi dot, okay, that's the induced map phi alpha dot gives an isomorphism of SL2C on C alpha plus C. We have this now in SU2 there is a special element, also taking the torus T, the Lie algebra of the torus T into taking diagonals into taking diagonals in SU2 into what I call T alpha. T alpha is going to be a Maxwell torus inside G alpha. Now let us look at the element, this element 0, 1, minus 1, 0, usually called W in SU2. This is the one which switches the two basic elements E1, E2, E1 goes to E2 and E2 goes to minus E1 or the other way around. That is to ensure that the determinant is 1. If I permute the basis standard transposition will have determinant minus 1, so I will have to put a minus 1 there. And then let me write phi alpha of W, I'll write as W alpha. This W is called the while group element, while element. In SU2, and I look at this image phi alpha W. What happens is, of course, W alpha is entirely in the center of the torus, and T alpha, and it actually normalizes the diagonal torus here. So W alpha of T equals T. In other words, W alpha normalizes T. With this notation, a statement I made, the theorem I stated last time is that the W alpha, alpha and delta generate the while group. Let me write W equal to, NT is the normalizer of T, and W denotes the NT by T. It's called the while group. Of G with respect to T. So you find that, let me write, I don't know if W, maybe I'll write S alpha, denote by S alpha, image of W alpha, W under the map, then the theorem I stated last time, that the S alpha, alpha and delta generate the while group W. Yeah.
So phi dot alpha is an isomorphism, and after that, can you repeat those arguments?
Sorry?
From phi dot alpha is isomorphism, that's fine.
Yeah.
Yeah, and from
Phi dot alpha. No, I mean just wanted to say that it takes the real algebra into this, because SL2 then I want to now forget about phi alpha. I go back to phi alpha. I look at this element 0, 1, minus 1, which is in SU2, which I call W, and then phi alpha gives homomorphism SU2 into G alpha. So I can take the image of phi alpha W, which I call W alpha, and W alpha T equals T. Reason is W alpha is the centralizer of T alpha, so it keeps T alpha in itself. Okay, and then what was I going to say? Yeah, I look at what I want to say is W alpha on kernel alpha. W alpha restricted to kernel alpha is the identity, because it centralizes that. Sorry, the kernel alpha is a codimension one thing. Notice that T equals T alpha times kernel. So because of that, W alpha T equals T. W alpha, see kernel alpha is on kernel alpha, W alpha is identity, and on T alpha itself sorry, on kernel alpha, yeah, and on T alpha, W alpha acts as x going to x inverse on the torus T. See, this corresponds to the maximal torus in G alpha. It corresponds to the diagonals here, and on diagonals W acts by taking any diagonal into its inverse. See, W that's inverse. You find that this becomes, so on T alpha on the codimension 1 torus, W alpha acts trivially. On the other part, which is kernel of alpha sorry, on kernel of alpha, which is codimension 1, W alpha acts trivially. On T alpha itself, W takes x to x inverse, T to T inverse. That's what's happening. Okay, and so W alpha is therefore takes T into itself, so it's a normalizer of T, and I can define the element S alpha by this, through this. I take W alpha, it's an element of NT, I look at its image and call it S alpha. And the statement theorem I stated last time was that S alpha, alpha and delta generate W. This set generates W. They are all elements of order 2. Notice that S alpha square is identity, because what S alpha does is identity on kernel alpha and it's T to T inverse on T alpha. So if you square it, it's identity on this as well as that. Therefore, it's identity. So S alpha square for every alpha delta. Okay, now I stated this theorem a little prematurely because I need some more preparation, but I'll go through that now before I go to the proof of the theorem. Now we have also seen that, remember, I also introduced this abelian Lie algebra, which is nothing but I times T. If H is I times T, then alpha restricted to H maps H into R. We know that the eigenvalues of any element in T is purely imaginary and their joint representation, and therefore in IT all the eigenvalues are real. So H into maps alpha H into R. So we can think of this, and alpha is determined. Maybe say I will use alpha also to denote the linear form on H. Alpha also denotes the linear form on TC, and therefore it gives you linear form on H. As it turns out, H is actually taken into R. So you have a natural map. There is an inclusion of delta in H star, which is home actually you can say there is an inclusion of the entire character group xt in H star, and delta of course sits here. So it goes into H star. So I will freely think of elements of delta as linear forms, real linear forms on H. The two things are the same because there is a nice injection there. Okay. So delta is contained in H star through its inclusion is factors through xt. Xt itself is contained in H star. Now that said, let me introduce. You see, each alpha is a linear form. So if I look at Let me write H sub alpha as the set of vectors V in H such that alpha H equals 0. V in H such that it's a hyperplane, codimension 1 subspace in a codimension 1 subspace in H. Let H1, H2, HL be a basis, an ordered basis of H. L is the rank of G. So, that is an ordered basis of H. And then this enables us to introduce a total order on H star on the dual. It is called the lexicographic order. Given by the basis. We say that a lambda linear form for lambda mu in H star, we will say that lambda is greater than or equal to mu if the first lambda greater than mu, if the first non-vanishing lambda hi minus mu hi is greater than 0. That is, start with lambda h1 minus mu h1, lambda 2 minus h2 minus h2. One of them, if lambda is different from mu, so one of them is non-zero. The first of this, which is non-zero, must be positive. Then I say lambda is greater than mu. It's a total order, as you can easily see. It's called lexicographic ordering. Okay, lambda hi minus mu hi. So, if lambda is greater than mu, if the first non-vanishing difference has to go from 1 to L, as I goes from 1 to L, the first non-vanishing difference is greater than 0. One less than equal to I, less than equal to L. Obviously, any two elements are comparable, so it is a total order on H star. Now, delta I denote by delta plus the set of positive elements in alpha greater than 0. We know that and delta minus alpha and delta alpha less than 0, then clearly we know that delta plus union delta minus is all of delta. Okay. A root alpha in delta is simple if it is greater than 0 and it cannot be written as the sum of two positive roots. That is the definition of simple root, and we denote by pi the set of simple roots. So now I am going to go into some depth about properties of simple roots. The first thing I want towards this is the following lemma. If alpha, beta are two roots, then the subspace sigma g alpha beta plus k alpha k in z beta plus k alpha is the root. Look at this sum. This is a g alpha stable at g alpha stable subspace of G. Because we are apply to prove it stable at G alpha, you can look at the Lie algebra of G alpha and see what happens to that. All this is stable under the torus, maximal torus. It is also stable under G alpha. If I apply G beta plus K alpha, notice that we have already G beta, G gamma, the bracket of these two is G beta plus gamma if beta plus gamma is a root all that you have to do is you have to take an element E alpha, E beta and E gamma, apply add t to that, add t E beta is beta t times E beta, add t E gamma is gamma t times that. So you find that applies to the bracket I am going to get beta plus gamma on t. I am multiplicating in additive notation, I am allowing myself to freely exchange to one from the other. So because of that beta, if beta plus gamma is the root, then G beta plus G gamma equals G beta plus gamma, and we also seen that if beta plus gamma is not a root, not equal to 0 and not a root, then G beta G gamma is 0, the same reason, because if you take x in this and y in this, you find bracket xy, add t on bracket xy is add t on x, the add t acts as Lie algebra automorphisms. So add t of x, add t y, which is, this will give you beta t x and that will give you gamma t y. So and you are going to get this, which is nothing but beta plus gamma t of bracket xy. But if beta plus gamma is not a root, there is no eigenspace corresponding to it, it is not a root, and I am also assuming it is not 0, there is no eigenspace corresponding to it. So there is no other way than bracket xy being 0. So and if beta plus gamma is 0, we have seen that E beta, so gamma is minus beta, we have seen that E beta E minus beta equals H beta, which is in the see this. Okay, now if alpha beta, then the subspace, it is clear now that this subspace is, if let us assume that beta plus alpha is a root, beta plus, okay. Now see what you get, therefore this space sigma, that it is clear that this lemma is clear. Apply g alpha to g beta plus k alpha, then it goes into beta plus k plus 1 alpha. Okay. Apply minus alpha, then it goes into beta plus k minus 1 alpha. So, it is of the same form. So, it is clear it is stable. And then I want to make the following statement: let k be the largest positive integer such that, largest non-negative integer with beta plus k alpha a root, and L the largest non-negative integer such that beta minus L alpha is a root. Then 2 beta alpha by alpha alpha equals L minus k. We have seen that 2 beta alpha by alpha alpha is an integer. I said that integer is precisely L minus k, where you go up, keep applying E alpha till you get to 0. The last one I call that E alpha power k. When I apply E alpha power k, it has become 0. The other side, E minus alpha power L takes it to E minus alpha power L plus 1 takes it to 0. That is the expression. And on the right hand side, E minus alpha power k plus 1 takes it to 0, but power k does not take it to 0. So, this is the statement I want. How do I prove this? This is immediate. Notice that these are all one dimensional spaces, eigenspaces. These eigenspaces are all one dimensional. We know that dimension g beta plus r q alpha equals 1 if beta plus q alpha is the root. Okay. So, each of the, now look at this as a representation of this 3-dimensional algebra. If I have a 3-dimensional algebra, then I know every representation is a direct sum of irreducible representations, and if you take an irreducible representation, the roots occur from some minus alpha to minus the roots that occur are from minus k by 2 alpha to minus k by 2 alpha to plus k by 2 alpha for some k. That is the way every one of them, intermediate one, occurs. So, but here, and if you have 2 irreducible representations, and if you have any, then so this at least one, either they have no common root whatever, or they have no common no common weight, or they could have, if they have a common weight, then that will occur with, we have dimension 2. Here everything applies is of dimension 2. So, what I want to say is from the theory of representations of SL2, we conclude that this is the representation of SU2 on sigma g beta plus k alpha k in Z is irreducible. If it is not irreducible, you will get a common weight which occurs in both irreducible representation. For instance, if they are half integers, then half alpha will occur in both. If they are whole integers, then 0 will occur the weight in both, and then the dimension will become, if they are non-trivial representations, then you will find that there also the dimension will at least be 2. So, because of that, this representation on this is irreducible, and then from that it is clear that, so if I and I know that from the fact that, so let us look at 2, let me sum up all the beta plus k alpha by alpha alpha summed over k in Z. This is nothing but on the element H, on which alpha H is 2. If I look at this element, then I know the eigenvalues are, starts with, they are all integers, so that it could be either and jumping by 2, so it will be q minus 2 etc. up to minus q, or yeah, that is the way it will be. And if q even, you will get some 0 in between. If q odd, you will get q minus 2 etc., and you will get 1 and minus 1 on the other side, and you end up in minus q. That will be the eigenvalues. And this is precisely the eigenvalue of H on the beta plus k alpha space. This is precisely that. From this statement will follow. See, your beta plus k is somewhere in between, it is there. So, you go this side up to q minus q, and that side up to plus q, so somewhere in between, or it could be on either side, here or here, similarly here or here. If you go one side, the other side, and from that a simple calculation will show you this. I do not think I am going to work it out on the board, because I am sure I will make a mess of it. So, I am assuming that is proved. Rest of it I will ask you to check. So, 2 beta alpha is equal to L minus k. In particular, if suppose beta plus alpha is, and this you know, so we also know that this is equal to plus minus 1 or plus minus 2 or plus minus 3. One thing that happens is the following: if 2 beta alpha by alpha alpha, let me put it like this, if 2 beta alpha by alpha alpha is greater than or equal to 0, let me write, is greater than 0, then beta minus alpha is a root. L minus k must be greater than 0, which means L is positive. So, on the other side you have to go at least to beta minus alpha. So, this is the conclusion I want. So, corollary if you like, if 2 beta alpha by alpha is greater than 0, then beta minus alpha is definitely a root. Okay. Now, with this lemma, so with this corollary, I claim if alpha beta are simple roots, 2 alpha beta by beta beta or alpha alpha, it makes no difference, is less than or equal to 0. Why is this? I am looking at the definition of simple roots. Let us see what happens. So, the proof of the claim, if 2 alpha beta by beta beta is, suppose it is greater than 0. If it is greater than 0, then alpha minus beta is a root. Now, I can assume by interchanging the roles, you can assume that alpha is greater than beta. So, alpha minus beta equal to gamma is a positive root. The point is that I start with 2 alpha beta, I want to say alpha minus beta is a root. I am assuming that alpha is greater than beta. If not, I can interchange the roles and beta can replace alpha and the other way around. So, alpha minus beta is a positive root, which means alpha equal to beta plus gamma. Now, beta is assumed to be a simple root. So, beta is positive root, gamma is also positive. So, alpha has been written as sum of 2 positive roots, which is a contradiction because alpha is simple. Since alpha is simple and beta gamma are greater than 0. So, the point is that the inner product 2 alpha beta by beta beta has to be less than or equal to 0 if alpha beta are simple roots. Now, we have this vector space H over R. On this, you have the various linear forms. Let us look at the kernel of alpha. It is a codimension 1 subspace. And H alpha splits H into 2 half spaces. Namely, H alpha, H minus H alpha equals 2 this is alpha equals 0, say. So, if this alpha equals 0, one side will be a set of vectors on which alpha takes positive values, on the other side the vectors on which alpha takes negative values. And what does notice that S alpha is acts as identity on on the space subspaces S alpha, and for if I take a vector S alpha of H alpha, minus H alpha. We have seen that in the torus it takes T to T inverse. So, in the corresponding Lie algebra, it takes x to minus x and takes to H alpha. I am looking at the torus T alpha, the torus in G alpha. So, that is what is happening here. In other words, S alpha is the reflection, it is a mirror reflection in the plane H alpha equals 0. I have this plane and I take an orthogonal vector H alpha as an orthogonal vector to the plane, and on that orthogonal vector H alpha equals minus H alpha. So, S alpha is the, that is why it is also of order 2, you know, S alpha is a reflection with respect to the inner product, the killing form restricted to H. We have seen that the killing form restricted to H is positive definite. On H is nothing but I times T. On T it is negative definite, and therefore it is going to be positive definite H alpha, and this S alpha is reflection. If you want to talk of reflection, you have to have the notion of inner product as well. So, in fact, this reflection S alpha on any H is by definition H minus twice alpha H and this is nothing but so that is how what reflection with respect to S alpha does. It takes H to H minus 2 alpha H by alpha alpha. When H is in the plane of, so that's it's a reflection given by that. Anyway, so what's happened is this: you have this vector space, and you have each alpha equals 0 defines a certain linear form. So, each plane is a plane like this. The color does not seem to splits up into various regions. So, ultimately what is happening is this: if I throw out all these hyperplanes, that is, if I look at H minus union, I called it H alpha, alpha and delta, you get a number of, it is a union of, disjoint union of convex cones. That is what is happening here. It is only the 2-dimensional I can draw pictures, and I-dimensional becomes more complicated. But anyway, see, the point is that if I take, say, alpha 1, alpha 2, alpha r, and alpha 1 greater than 0, alpha 2 greater than 0, etc., alpha r greater than 0, each of them is a half space, which is a convex thing, it is a cone, because multiplied by positive real, it stays where it is, and so the intersection is. You can also, if I take alpha less than or equal to 0, that same thing as minus alpha greater than 0. So, some plane or other, it is always greater than 0 thing, that is how you get a cone. Each of these, so it breaks up into connected components, disjoint union, each H alpha is a cone with vertex at the origin, so open cone. I'm going to throw out with 0 as vertex. 0 itself is not in the space. Okay, so this is what has happened. Now, oh yes, I have to. I said I've already proved for you that if I take any lemma here, every root is an integral linear combination beta equal to of simple roots with all coefficients non-positive or non-negative. The pi on my basis of H star. The delta, observe that delta generates all of H as a vector space. Delta clearly generates all of it as a vector space, because if I take a common 0 of all the deltas, that is 0, because we know that at the Lie algebra level, the action, the torus representation is the Lie algebra torus is represented faithfully on the Lie algebra G, and if you take the kernel of linear forms alpha, all the linear forms alpha and delta, you get 0 as the space, which means deltas certainly span the entire dual of H. So, for every H in H, there exists alpha and delta with alpha H not equal to 0. So, delta generates all of this. Once, and if I prove this first statement, every root is a combination of this kind, then it will prove that pi forms a basis. Oh yes, I also to show that pi's are linearly independent. We'll come to that. Okay. The point is this: I know that pi. This statement I have to prove that every element, every root is a linear combination of this kind. So what do I do? Suppose I argue by induction. It's enough to prove it for roots beta which are, so let me prove this. Suffices to show that if beta greater than 0, beta equals sigma m beta alpha in delta with m beta alpha in pi greater than or equal to 0. See, there are only finitely many roots and there is a total order. I can therefore argue by induction. Suppose I proved it for all roots up to a certain point, there are only finitely many of them, then I have to prove it for the next one in the total order. So, induction, how does it work? So, if alpha is the least element, it is simple, because it's the least element. That means what? It cannot be written, if you can write, if it's not simple, it becomes some beta plus gamma, in which case alpha will be greater than both beta and gamma, beta gamma positive. So, alpha naught is the least element if alpha is in pi. So, for which therefore the statement is true. Suppose you proved it for suppose statement holds for all beta in delta plus with for all beta and delta plus less than with beta less than, say, beta prime with beta prime less than beta. Then let us look at beta. If beta is simple, we are done, there is nothing to prove. Beta is not simple, if beta not simple, then beta is gamma plus delta, where gamma delta are less than beta. Each of them is a non-negative linear combination of simple roots by induction, and therefore the sum is a non-negative combination of roots. Statement holds for gamma delta, induction hypothesis, hence for beta. So, that statement is proved. Next, I want to prove that pi are linearly independent. How do I do that? Suppose there is a linear combination. Suppose you have some sigma m alpha, alpha equal to 0. Some of these coefficients will be positive and some of these coefficients will be negative. They are all real numbers. So, I can write this as sigma a alpha alpha with alpha in one side delta 1 equal to sigma a beta beta with beta in delta 2, delta 1, delta 2 disjoint. I can write like this with a alpha, a beta, all the a alphas greater than 0, greater than or equal to 0. And now take the inner product of this with itself, which will give you a positive thing, and that is the inner product of these two. But on the right hand side, alpha beta is always negative, because your two simple roots are not equal, their inner product is negative. So, this sum, this side the sum will add up to something negative, and that side it will be something non-positive, and the left hand side will be strictly positive if the alphas are not 0, not all. So, which is the contradiction? Sigma, I take the inner product sigma a alpha alpha we know that 0 is less than this. If there is a linear combination, I will written it like this, at least some a alpha will be non-zero, I take the alpha to be one of these alpha and delta 1 to be non-zero, otherwise I can interchange the thing again. So this is equal to sigma alpha in delta 1, and this side it will be sigma alpha in delta 2. Let me write here beta, and that gives me sigma A alpha A beta and notice that this is always less than or equal to 0. Less than or equal to 0 will give a contradiction. Okay. Now, let me get back to the theorem I was after. The point is this: you have this. What I will do is this: let W prime be the group generated or let me call it W naught be the group generated by S alpha in delta alpha in pi, and W1 be the group generated by S alpha in delta. What I am going to do is the following. I look at, first observe the while group. So we have here W1, W naught contained in W1, contained in W. Observe that W acts on the set of roots, and therefore on the set S alpha in delta. We must also remark here that S alpha is same as S minus alpha. Okay, I look at therefore acts on the set S alpha. Observe that, so W permutes the hyperplanes which are called H alpha and delta, and hence stabilizes H minus union H alpha and delta. And the connected component of all this are cones, as I have already remarked. While chamber by definition is a connected component of H minus union H alpha. That is by definition of while chamber. Okay. So, if C is a while chamber, we denote by C closure. Sometimes, okay, I will call the C closure is the closed while chamber. What we will show is the following. We will show that W naught acts transitively on the set of closed well chambers, and W acts simply on the set of open well chambers. In fact, I don't, on set of well chambers, also closed well chambers. So if I prove this statement, these two statements, which will imply W acts simply and W naught acts transitively, this will imply W naught equal to W. So both of them permeate well chambers. One of them acts simply, the other acts transitively. So you find that given any element in W, there is an element in W naught which take a fix a chamber C bar, and pick an element G C bar equals G prime C bar for some G. For some G prime in, start with G in W, then I know the G primes for some G prime in W naught. Then this happens, given G there is a G prime, and then you look at G prime inverse G C bar equal to C bar. That means that this element, so now this is an element of W, because G prime anyway is in W naught, which is contained in W. So G prime inverse G fixes the chamber. But to say that the group W acts simply is to say that G prime inverse G C bar equals C bar implies G, this is equal to 1. So that proves W naught equals W. So in other words, the while group is generated by reflections coming from simple roots. It's also the same as the group generated by odd reflections coming from all roots. Whether you take only simple roots or all roots, you get the same group. The group generates the while group. So these are the two statements one has to prove. Now, how does one prove this? First, that it acts simply. You suppose W is in W and WC bar equals C bar. This implies WC equal to C as well. The interior will go into the interior. Okay. If WC bar equals C bar, the interior of W is a homeomorphism. So it goes to W, the chamber is fixed. Now pick an element, so the chamber has a number of walls given by various roots. The chamber is given by H in H, alpha H greater than 0 for a subset for all alpha in a subset in delta 1 contained in delta. That's what it's going to look like. Now let's look at, pick an element H in this, chamber is given by this, pick an element of the chamber, chamber C is given by, pick H naught in C, and let's look at sigma W power R H naught as R varies. It's a finite group, so there's only finite sum. If I look at this sum, on every one of these elements alpha is greater than 0, so you find that this element is fixed by, so if I call this element H1, H1 is fixed by W. Okay. H1 is fixed by W means what? That means if I look at the W1 acts as W1 on T equals 1 for every T exponential of IT H1. The fact that H0 is a connected component also implies that if I take this element H1 in C, note H1 is in C because all these alphas are greater than 0. Notice one other thing here, H1 is in C implies alpha H1 not equal to 0 for any alpha in delta, because we have taken the complement of all the alphas not equal to 0 and I take the interior of the chamber, H1 is in the interior and therefore alpha H1 cannot be 0. I have thrown out all the planes alpha H for every alpha in delta, so because of that H1 is in C implies that alpha H1 is not equal to 0. Now let's look at the, we are looking at, consider now the subgroup G in G such that add G of H1 equals H1. This group is a centralizer of, yeah.
H1 is defined by,
Sorry?
H1, last line,
H1 is fixed by W because I have added W per R, R goes R in Z. If I apply W to this, this is just a permutation of the powers of W. So it's fixed by W. H1 is fixed by W. So H1, so I have this element is fixed by W. Now we look at the set of elements in G which fix H1. This is same thing as centralizer of X of this torus, centralizer of U in R, and hence its closure which is the torus. And what kind of torus is it? I have taken the element H such that alpha H1 is not 0 for any H1. So if I take the corresponding torus, it's something on which no character is trivial. That is, and that implies it has to generate the whole torus. Implies it is centralizer of T itself, because this, if you look at this as a closed subgroup generated by that, is going to be the whole torus. If it fixes this element, it fixes the entire torus is what I am saying. If it fixes one element in which alpha H is not 0, then it is going to fix the and all elements. So it becomes centralizer for T, which is T. That means our element W1, which is something in NT. So I mean, yeah, W1T, which comes from, this is image W1 tilde say. So all this goes on to say that W tilde is in the torus, W1 tilde, but that means W1 is identity. NT by T is in while group, W1 becomes identity. So if something keeps a chamber in itself, then the element has to be identity. So that proves that the second statement, that W acts simply means if it fixes something, it has to be the identity, the element. That's what simply means. How do I prove the transitive action? That is done as follows. Let me introduce the following set. Let S be the union alpha beta linearly independent it's a union of codimension 2 subspaces. If I take two linearly independent alpha beta, then the corresponding hyperplanes H alpha H beta is a codimension 1 each, and the intersection is codimension 2. So these are codimension 2 subspaces, and that means, this implies, if I look at H minus S, remove S from H, this will remain connected. If I remove a codimension 2 subspace from a space, then the space remains connected, because take 2 points outside, they intersect with a plane, and they take a plane passing through these two, then the codimension 2 subspace will intersect the plane in a codimension 2 subspace, which means 0. So there will be only the intersection will be removing 1 point. You have 2 points in the plane, you have removed a point from the plane, still they can be connected. Okay. So the complement is connected. You have to argue with finite number of planes, which means you are removing finite number of points. That's what you do to amount to. Okay, now H minus is connected. On the other hand, if you look at the set of, let me denote by C0, the set H alpha H greater than or equal to 0 for every alpha in pi. I claim that this is a chamber. This is easy to check. You have to check, take any other, to prove that it's a chamber, you have to prove that if I take any other beta, if I look at beta H, throw out beta H, then how do I say it? Well, you can check that it's not difficult. Okay, I don't quite see the argument just now, but it's an easy argument. You find that C0 is a chamber, and once you know it's a chamber, what happens is this: if you look at this chamber and take one of the walls, alpha, okay, and take a point. What I want to say is this: yeah, the chamber is here, and I take one of the walls. That means I take one of the alpha equals 0 with alpha and pi. When I'll throw out this, but if I reflect with respect to S alpha, if I take a neighborhood like this of that, then it will get into a neighborhood like that. So when I do that, what happens is this: the union becomes an open set. This applied S alpha, you get an open set. That is, union of two chambers will contain a neighborhood of this point. And now you only take the group generated by that and saturated by that, then what you find is that the set you get is open. So get union C0 minus S, union WC0, W in W0 of WC0 is open in H minus S. It's open even in S, therefore it's open in H minus S. Interior points give no problem. For interior points of the cone give you no problem, but points on the boundary of the cone, which means you're omitting intersections of two planes. So anyway, those boundary points, if you apply the reflection, you get an open set like that. So this is an open in H minus S. On the other hand, it's obviously C naught is closed in S, and you're only taking a finite union, so the union is closed. It's open and closed, so that means it's closed as well. So implies it's equal to H minus S. So W is that shows that W naught acts transitively on the set of chambers. So that proves the statement we made that the value W is generated by reflections. And in fact, we can choose the reflections to be reflections in simple roots. So that proves the theorem. Okay, this is where I'm going to stop. I've already exceeded my time by 2 minutes, but stop here.